this one, okay? Equivalent time. What's the definition of this? How can we utilize simplify B method, okay? And we have already discussed in quite detail how to calculate the SF, right? SF, the primary consolidation or the final consolidation, right? Settlement, the final settlement due to primary consolidation, okay? And for calculating SF, we should know the final stress state here, final stress state, the initial stress state, okay? Two slopes, okay? CE and the CC. And if it is on the point 4, we use this equation because it will surpass the pre-consolidation stress point here, right? If it is on the point 2, which is on the OCL line, over consolidation line, we use this simple one. Again, we have the slope, the final stress state, the initial stress state, right? And for the pre-consolidation point, we from the point 1, from the pre-consolidation point to point 4, both of them locate on the NCL, normal consolidation line, so that we only use CC, right? The initial stress state again, okay? For the unloading one, from point 4 to point 6, the SF will be smaller than 0 because this is unloading, or we call it a rebounce, okay? A rebounce stage. The stress is released, okay, from a larger value to a smaller value. So again, for the reloading, we use this one and the final initial slopes, okay? SF should be quite simple. And for calculate the S-creep final, actually, we discussed different cases. For different cases, we have different formula to use, right? If the final point is on point 4, which means the final point is on the NCL line, right? We just use a simple equation. The slope now is C alpha E, okay, C alpha E. C alpha E means log time, epsilon, or void ratio, okay? C alpha E is from void ratio, okay? If we use C alpha epsilon, it's from the epsilon, the strain, okay? C alpha epsilon is equal to C alpha E divided by 1 plus E0, okay? This one, you should be very familiar with it, okay? Sometimes in the question, we only give you C alpha E, okay? Sometimes we only give C alpha epsilon, okay? You should be very careful. It's a very small difference, okay, in the subscript, but the calculation result will be quite different, okay? So C alpha E is the slope here, the slope of this part, okay? This is C alpha E. And actually, TE, the equivalent time, is equal to T minus T0, right? So that this equation can be further simplified to C alpha E divided by 1 plus E0 log time, okay? Multiply the H, the thickness of the soil layer, because TE is equal to T minus T0, right? T0 cancel, and T0 is equal to 1. So we can further simplify it to this one. So when the final point is on the NCL line, we just use this equation to calculate the S-creep final, right? And if the case, in this case, the final state is on the over consolidation line, for example, point 2 here, we normally use this equation to calculate S-creep final, okay? This equation. The only thing we need to calculate more is TE2, is the equivalent time at point 2, okay? How to calculate? The equation is here. Equation is here, okay? This equation seems quite complicated, okay? Quite long, but actually every parameter we can calculate one by one and with very clear physical meaning, okay? We derive this equation from this one, okay? This one is the so-called constitutive model proposed by Professor Ying, okay, more than 20 years ago, okay? I also discussed with you why this equation is always valid or always correct for any point on this figure, okay? In last lecture, you can refer to the recording again if you are interested why this equation is valid, okay? Anyway, we have this equation, we can get the expression or the equation for the equivalent time for any point. So this equation is what we are going to use, okay? So to get the TE2 and put into this equation here and calculate the S-script final when the final point is at the over consolidation line, okay? This is a case. Then for the 0.6 or 0.5, they are similar actually, because all of them are on the OCL line, okay? So we can get the TE5, TE6, okay? We can expect that the TE6 will be much larger than TE5, okay? Than TE5, because it will take a much longer time for reaching 0.6 by creep, okay? We can expect that. Okay, so in last time tutorial, we go through one example, right? And we already see that sometimes the TE6, the equivalent time can be a very large number, okay? So we also discussed how to calculate the S-script delay. S-script delay actually is one part of S-script final, okay? One part of S-script final, which means when the T is larger than TEOP at field, this new parameter, okay, represent at this time point, U is equal to 98%. Right? So when T larger than TEOP at the field, how much further creep occur? Okay, this further creep is S-script delay. Okay, the so-called delay means the only calculate the creep after the average degree of consolidation larger than 98%. Okay, so it is one part of S-script final, so that we can just use the equations we discussed for S-script final to calculate S-script delay, right? So you can see, for when the final point is at 0.4, which is on the NCL line, right? We just use this equation, the equation 2, to calculate S-script delay. So as we said, S-script delay is one part of S-script final, right? So this equation, actually, we get it from C alpha E divided by 1 plus E0 log T. So this T means the present time, okay? The present time minus C alpha E log TEOP at field, right? Then we get this one, okay? Very simple, right? And multiply the thickness, okay? Because the S-script delay is only one part after the T is larger than TEOP at field, right? So we get this equation 2. Similarly, when the final point is on 0.2, which means the point is on the OCL line, right? 0.6, 0.5, they are the same, okay? So you can see here, we calculate this part first. This is S-script final, right? Minus, okay, we just replace this T by TEOP at field, okay? So then we can get the S-script delay, right? We just use the equation for S-script final to get S-script delay, okay? So we discuss how to calculate script final, script delay, and SF, right? And we also present you a so-called simplified method to calculate the radial consolidation degree, UR. Okay, this is a simplified method, the so-called simplified method. Okay, for radial consolidation, we present discuss with you using the chart method. Okay, design chart method to determine UR from TR, right? But here we present a more mathematical way, okay, to calculate the UR from TR, also considering the effect of the so-called smear zone, okay? The smear zone, because we penetrate the PVD, okay, using the mandrel, it will disturb the soil surrounding, right? The soil after remolded or after disturbance, the K permeability of the smear zone will be smaller, become smaller, okay, than its original state. So Ks will be smaller than Kh. This S means smear zone, okay? We discuss here with this schematic drawing here, right? And I also remind you, this Re is equivalent radius of the column, of this column. This is a column. So half of it is equal to Re. Here, to calculate TR, we use Re at the denominator part. But in the chart method, actually, we use D. We use the diameter, okay? We use diameter. So don't mix them up, okay? In the simplified method, we use Re, okay? This is a part some student will not pay attention, okay? Use the wrong parameter here. Okay, so example 5, 6, and 7, 8, we already discussed, okay? Example 9, you can go through by yourself. And today, let's see together and discuss together the example 10, okay? Example 10 actually is a very important example. And later, you are required to submit the assignment, right? After we finish the lecture 2. So in next week's tutorial, I will go through with you the assignment 1, okay, for the lecture 1. So today we just focus on the example 10 first, okay? So maybe give you 8 minutes to go through the example question body, okay, first. All right, maybe we start a little bit earlier, okay? And as I mentioned, I will go through with you the assignment, what you need to pay more attention for the assignment, okay? And I will open one link, okay, in the Blackboard. Then later you can submit your assignment directly in the Blackboard, okay? And let's start here with example 10. And figure 6 shows a layer of Hong Kong marine clay 8 meters thick on a layer of alluvium 7 meters thick. Okay, sea level is 5 meters above the Hong Kong marine clay. Let's see here. Okay, Hong Kong marine clay here 8 meter and alluvium 7 meter at the bottom. Okay, and you can see one more thing. Okay, the alluvium for the bottom boundary is impermeable. Okay, the information here actually has been given. It's impermeable. Here is impermeable. Here is impermeable. So for alluvium, the water can only move vertically. Okay, first one, only move vertically from bottom to top, from bottom to top. Okay, because the bottom boundary is impermeable. And for the Hong Kong marine clay, let's see the soil element at this interface, because the water can only move upward from alluvium to marine clay, okay, like this. So actually the water inside the Hong Kong marine clay cannot go down, okay, cannot go down into the alluvium, okay, because the water flow direction is only from the bottom to top. So that for the alluvium, the maximum drainage path length is 7 meters, okay, right? The maximum is from here to here. This length is 7 meters, the so-called D, right? If you still remember the D, the maximum drainage path length, okay? And for the Hong Kong marine clay, even though below we have the alluvium, okay, not an impermeable soil, but the water can only move upward, okay, can only move upward, like this. Okay, so the in vertical direction, the maximum drainage path is also equal to the thickness of Hong Kong marine clay layer, okay, which is equal to 8 meters, right? 8 meters. So this is the first thing. And the second thing is, for Hong Kong marine clay, we have the vertical drain. We have the vertical drain are only installed through layer 1, okay, ended on the top of layer 2, which has been drawn here. Okay, this is vertical drain. So for Hong Kong marine clay, except the vertical direction of water flow, we also have the horizontal water flow, right? To the vertical drain first, then move to the top surface, then flow away. Okay, this is another direction of the water flow in the first layer here. So for Hong Kong marine clay, this is 2D condition, okay, 2D asymmetric condition for the consolidation. And for the alluvium, we only have 1D consolidation problem, okay? This is the conditions, okay, the difference between these two layers. So for the layer 1, CC has been given, okay, also here CC, CE value, okay, gamma saturated, okay, the unit weight when saturated, void ratio, initial void ratio, okay, and the pre-consolidation effective stress, pre-consolidation, ZP means pre-consolidation, this prime means effective, okay. For the layer 1 is equal to 60, and for the layer 2 is equal to 300. So C alpha E here. Again, sometimes we just give you C alpha epsilon, okay? You need to know how to convert with each other, okay? Between each other. So here we have C alpha E, T0 is always equal to 1 day. And CV, the coefficient of consolidation in the vertical direction, okay? And CH, CR, actually they are the same thing, okay? Horizontal or radial equal to 2.4, okay? You can see that the CH or CR is 2 times larger, okay, than the CV. So we already discussed why the horizontal permeability will be larger than the vertical permeability, right? In our previous lecture. So we have all the parameter here. And a uniform sand fill layer is assumed to be placed on the seabed gradually in 6 months, okay, up to 6 meters above the sea level. So this sentence implies 2 important messages. The first one is the construction time is 6 months, which means half a year, right? And the target value, target height of the sand fill layer is 6 meters above the sea level, which means the total height of this sand fill will be 5 plus 6. In total, 11 meters, okay? This is the height or thickness of the sand fill layer. And the unit weight of the sand fill is here 20. And the vertical drain is installed in square pattern at a spacing of 1.2 meter and the equivalent diameter. How to calculate? Okay, this equation has already been given. Okay, for the square pattern, we use this one. But for the triangular pattern, we use another one. Okay, you can refer back to the previous slide. And the drain diameter, D well, okay, this W means well. dW is equal to 0.1 meter, okay? But actually what we need is RW, the radius, okay? In the simplified method, okay? We can see later. And the data for the smear zone are here, the DS, the KS, KH, okay? KH is horizontal permeability, right? And KS is permeability at, this KS is the smear zone, okay? The permeability at the smear zone, okay? Permeability at the smear zone. So let's see. The smear zone permeability is half of the horizontal permeability of the soil. Half, 0.5, right? Becomes smaller, right? Becomes smaller. So the first sub-question is to calculate the effective vertical pressure on the seabed due to the sand fill at 6 meters above, okay? Effective vertical stress due to the external loading, okay? The surcharge, okay? The surcharge. So if we have a total thickness of 11 meters for the sand fill, okay, let's see. So the 6 meter will be above the sea level. So we will use total unit weight, which is equal to 20, which has already been given here. And we also have 5 meter submerged underneath, okay, the sea level. So we should use the saturated effective unit weight here. Use the 20 to minus the unit weight of the water, gamma W, right? Gamma W. So we divide it into 2 parts to calculate the effective stress change due to the surcharge, right? We get the result here. Okay, we divide it into 2 parts. And for the second sub-question, to calculate the initial vertical effective stress at the middle of layer 1 and layer 2, okay? The corresponding strain are 0, okay? We assume the corresponding strain at the initial point are equal to 0. Again, we just choose the middle point of each layer, the stress state at the middle point to represent the average stress of this soil layer, okay? Let's see. For the Hong Kong marine clay, the middle point, how can we calculate it? we are going to calculate the initial, okay, the initial without or before, okay, the sand fill layer is placed, okay. We just want to calculate the initial value. So for the Hong Kong marine clay layer, we on top of this middle point, we only have the half layer of the Hong Kong marine clay on top, right? So the thickness or the height of this half layer is equal to 4. Then multiply the effective unit weight, okay? Effective unit weight again. The total one for the Hong Kong marine clay is 15.5 minus the gamma W 9.81 to get the initial effective vertical stress of the center point of Hong Kong marine clay, right? And for the second layer, the so-called alluvium, we have the whole layer of Hong Kong marine clay on top, plus half layer of the alluvium on top, right? So we have two parts. The first part is Hong Kong marine clay, and the second part, the thickness is half of 7, right? Half of 7. 3.5 multiplies the effective unit weight of alluvium layer itself, right? So we can again get this result. All the unit weight here are saturated effective stress because all the soil here is submerged, okay, under the sea level, right? So we use this effective parameter. Then for the third sub-question, to calculate the strength corresponding to the constant pre-consolidation strength pressure of layer 1 and layer 2. Actually, the pre-consolidation stress has been given here for both of these layers, right? We already know the pre-consolidation pressure here. So you can see that the initial point here for the initial stress state here is only 22 point something is smaller than 60 kPa, right? And again, this 81 is also smaller than 300 kPa, right? So the pre-consolidation stress for both of these layers are larger, okay, than the initial state. So how to calculate the strain at this point, at the pre-consolidation stress, okay? We can know that we only utilize the slope, CE, is good enough, right? Because all of them are smaller than the pre-consolidation stress, which means they are all in an over-consolidated state, right? So CFIE we know, and the final stress here is the pre-consolidation stress, and the initial stress here is the current state, the initial value here. So we can easily get the result here for the Hong Kong marine clay layer, also for the alluvium layer, right? We can easily get it. We only utilize this part, okay, because both of them are on the over-consolidated state, right? Then let's see the fourth sub-question. To calculate the final primary settlement for layer 1 and layer 2 under the loading, okay, under the loading of the charge above, okay, no further division is okay, okay. No further division means we can only utilize, okay, the middle point to represent the average state of the whole layer. Okay, so here actually one more thing I want to say is because we assume the corresponding strain at the initial vertical effective stress is equal to 0, okay, is equal to 0. Actually, the strain at the pre-consolidation pressure is equal to 0 plus 0 plus, okay, plus this value, 0 plus this value, 0 plus this value, we get the result, okay? We have an assumption, okay? And for the fourth sub-question, we are going to calculate the primary, okay, the primary consolidation settlement for both two layers, right? And let's see for the first layer first. The initial value is here, 22.76 plus this value. This value is due to the same field, the surcharge loading, right? Due to the same field. So the final effective stress is equal to this value, which is larger than the pre-consolidation stress, which is equal to 60. Okay, so to calculate SF, we know now the stress point is on the NCL line, right? Because the final state is larger than the pre-consolidation stress here. So we should use the full equation. We get the CE to surpass the pre-consolidation strain. Then we use CC to calculate how much settlement happened from the pre-consolidation strains to the target point. Okay, this is the second item. So we can just input all the parameter here, This one we already calculated already, right? And CC value here, and the final stress, the initial stress. Then multiply 8. So this is SF due to the surcharge for the first layer. And for the second layer, we do the same thing, okay? But one thing is different. The final stress state is still smaller than 300, right? You see that it's still smaller than 300, which means we still use only one item is enough. CE, the final stress state, the initial stress state. We get this value, okay? Multiply, the thickness is 7, okay? Here, not 8, okay? Here, sometimes this kind of small difference, okay, will be, maybe some student will not pay much attention, okay, to these small details, okay? We should be careful. And for the fifth sub-question, to calculate the values of the average degree of consolidation of layer 1 and layer 2 on the loading, okay, under the surcharge, at the time of 50 years from the beginning of the loading. Okay, I saw one question in the chat box. It has to be 7, right? Yes. Yes, because we use the middle point stress state to represent the whole layer, okay, as an average value. We get the strain for the whole layer, average strain, okay, we can say that, average strain for the whole layer, then multiply the thickness of this layer, okay? For alluvium, it's 7. For Hong marine clay, it's 8, okay? So actually, all the strain we calculate here in this bracket, we can call it average strain, okay, or average strain. Then we multiply the total thickness. So for the fifth sub-question, we need to calculate the final settlement at the time of 50 years. At the time of 50 years. So what we need to calculate the, we are going to calculate the average degree of consolidation, okay? Average degree of consolidation at the 50 years. So what we need here, we want to calculate U, we should know the TV or TR, right? If we have the vertical drain installed, we should also know the TR. Then how to calculate the TV and TR? We need to know the T, okay? The T here actually is equal to 50 years, but we have construction time, we have construction period, which is equal to 0.5 years. So the first thing we need to do is to do the correction of the construction period, right? So we just use this equation here we discussed before, right? When T is larger than the construction time, TC, here obviously, okay, obviously larger. So we use this one. We just use T minus TC over 2 here, this value to do the correction, okay? Later, we will all use this time rather than use 50, okay? This, we call it corrected time due to the construction period. Okay, so this is the first thing. We do the correction, and we use it. We use this corrected time to calculate TV. You see, we use this one to calculate TV. CV we know D again. Okay, D for the Hong Kong marine clay, the D is equal to 8. Okay, is equal to 8 because we already discussed that the longest drainage path length for Hong Kong marine clay is from here to the top. So the length here is equal to 8 meter. Okay, 8 meter. So we use 8 to represent D here. So we get this result. The bottom is impermeable. Okay. Here we say it is impermeable, but it's not very accurate to say. Okay. Actually, the soil alluvium must be permeable, right? Must be permeable, but the water can only go from the bottom to top. This is the only water flow direction. Okay, in the vertical direction. Okay, from bottom to top. So this is TV. We get it. And to calculate the UV, let's try this formula first. You can see here, this formula. We get the result, which the UV is equal to 0.9189. It's larger than 0.6. Okay, it means we use a correct equation. Okay, if you find this one is smaller than 0.6, actually we should use this equation to calculate the U. Okay, we calculate the U. So sometimes we just try it first. Okay, so we use the correct one. We get this result, which is larger than 0.6, but still smaller than 98%. Okay, still we cannot say it finished the primary consolidation. Okay, or we can say that the TEOP at field has not been reached when T is equal to 50 years. Okay, so we discuss this later. Okay, and for the first layer, we also have the vertical drain installed, right? So we should calculate the TR and to get the UR, right? To get the UR. So the UR is equal to this equation. We need to get the TR and we need to know the M. The M actually is this long equation here, right? So we need to know the N, the S, KH, KS actually this ratio we already have in the question body, already be given, okay? So what's N and what's S? N is the ratio between equivalent radius of the column over the radius of the well, okay? This value has already been given in the question, right? Here, RE is here, this value, but in the question, okay, the information actually is DE, So we use the value of DE divided by 2, okay? We get the RE, right? And the RW already be given here from the DW, okay? From the DW. So you see here, DW here, DE here, right? We get the RE and RW. So the S is equal to the radius of the smear zone over the radius of well, okay? The S is equal to 3. And actually here, the N, we don't have the unit. This M, meter, okay, should not be here. Should be, okay. I will delete it later, okay? Because this N value is a ratio. It should not have the unit, okay? It's dimensionless. So this M should be cancelled, should be deleted here, okay? And the TR, we again use the corrected time to calculate TR. Again, I just want to remind you, RE is here, okay? Not 2R square, okay? It's only R square, okay? RE square. So we can get the TR value here. Then we know all the parameter, TR, M, NS, everything, okay? We know everything already. So we can calculate the UR, which is equal to 1. So UR if equal to 1, this item equal to 0. Again, 1 minus 0 is equal to 1. So at 50 years, actually, the average degree of consolidation for the homomarine clay is equal to 0, which means the primary consolidation actually has been totally finished. Okay, we can say that. So how about the layer 2? Okay, for the alluvium. Okay, we just skip this part first. To calculate the average degree of layer 2, we know the height is 7 meters. Okay, we also do the same thing. Okay, to correct the construction period, we get this value and we calculate TV based on the corrected time. Okay, it's same. The only thing different is the D here, the maximum drainage length, right? The bottom is truly impermeable because it is a bed rock, right? So UV here, okay, we use the correct equation to calculate, which is larger than 0.6. Also, it's smaller than 98%, okay? Smaller than 98%. So for the, here actually, we calculate the TEOP field for the second layer, okay, which will be used later, okay, we discuss later. So here actually, we already get the final degree of consolidation for layer 2 already, okay, which is equal to this value, right? This is simple. This is much more simple because the water can only move vertically, okay? The vertical drain is only installed for layer 1, okay, rather than not for layer 2, so it's simple. So let's see the sixth sub-question. Calculate the creep settlement and total settlement. Okay, the creep settlement as creep. As creep. The total settlement actually is as total, okay? And we need to calculate the TOP at the field. Why? Because we need to calculate as creep delay, right? As creep delay. As creep include two parts, as creep final, as creep delay, right? So for layer 2, we also need the TUP at field and the total settlement of 2 layers together at the time 50 years using this simplified hypothesis B method. Okay, alpha is equal to 0.8. So the total settlement of these 2 layers, we just do a simple superposition. The sum up, okay, sum up the total settlement of layer 1 and the settlement of layer 2. We just sum them up, okay? So let's see. First thing is to calculate the TEOP at field for layer 1 and for layer 2, right? It will be difficult for a little bit troublesome, okay, to calculate the TEOP at field for layer 1 because we have UR, we have UV, right? TR, TV. Both of them, okay, are from T. Okay, this T actually is what we want at the EOP, okay, at field. So when overall consolidation degree is equal to 98%, which is equal to this one, right? And these two are function of T, right? Function of T. So when 98% is achieved for the overall consolidation degree, what is this T value? Okay, what is this T value? This T is TEOP at field, right? We want to calculate this value. Okay, we want to calculate this value. So we just use the try and error method. Okay, try and error method to try to determine this TEOP at the field. Okay, you need actually we need to maybe try for several times. Okay, to gradually reach this value. Okay, the value here is equal to 1.3 years. Okay, for example, you try 10, you try 1, you try 5, then slowly, gradually, you get this approximate value for TEOP at field, then the overall consolidation degree is equal to 98%. 98%. Okay. So normally in your final examination, this value will be possibly given, okay, in the question. So possibly will be given, okay, normal routine, okay, will be given. So you don't have to spend much more time on try and error, okay. So here we just directly give you the result 1.3 years, and you can see if we have 1.3 years, we use this into the t value here, okay, get the UV. Again, we calculate TR, then get UR. You see the final U is almost equal to 98%, okay? So this is for the layer 1. And for layer 2, UV equal to 98%, we directly to use this one to replace this value here. Then we can get a TV. TV is equal to 1.5. Then we have TV value. We can easily calculate this T, right? CV, TC, D, we all know already. So this T is equal to, this T actually is TEOP at field 2, okay, for the second layer. So is this large value, okay, more than 100 years. So you can see that the end of primary consolidation for the alluvium take quite a long time, okay? So we get the TEOP already for both layers, right? So the crypt settlement for these 2 layers, first one, we know the final, we should calculate the final stress first, okay? Final stress point is larger than the pre-consolidation stress, so that we will use the case of 0.4, which is on the NCL line, okay? So we use this equation, or we further simplified to this equation, okay? So you can get this result easily, right? Easily. This T here is 50 years multiplies 365 days per year, okay? Then multiply the thickness of the first layer. The important thing is which equation you want to choose, okay? Because it's on the 0.4 case. So we use this equation. And the TEOP we already get, right? And for the crypt delay, we use this equation, okay? Based on the 0.4 case, right? And TE plus TE, T0 plus TE actually is equal to T, okay? Because TE is equal to T minus T0, right? 0, 0, cancel. So here, the upper part is equal to T. And the lower part is also equal to TEOP at field, right? The lower part is equal to this one. So we put the value here. The TEOP at the field, 1.3 years, T, 50 years, right? No problem. Then multiply the thickness of the soil layer, we get the S-crypt delay for the layer 1. Okay, then we just use this simplified hypothesis B method to get the final result. U is already, okay, for the first layer, U is already being calculated, okay, which is equal to 1, okay? And the final state, final settlement, SF, we also calculated before in the, here, the SF for 2 layers here, right? We just use it. Then we get this result. And for the layer 2, we calculate here, we see that the final stress is still smaller than the pre-consolidation stress. So that is on the OCL line here, right? It's OCL line rather than the NCL line. So we will use something different. Firstly, it will remind you, if you want to calculate the S-crypt final, you should know the TE2 value. The so-called TE2, actually you can use, don't use TE2, okay? 2 is just a symbol. It can be, it just want to tell you it is on the OCL line, okay? OCL line. So the strain at the point 2 is here. Actually, we calculated already this value. And this one is pre-consolidation stress. Pre-consolidation stress, the corresponding strain, okay? Corresponding strain on the corresponding strain of the pre-consolidation stress, okay? The corresponding strain for the pre-consolidation stress state, okay? So we calculate it here. We only use this part. It's enough because all of them are on the OCL line, right? So we get these two values. We input them here. V we know, C alpha E we know, everything we already know. T equal to 1, right? And the stress state the pre-consolidation stress for the layer, okay, the second layer. And this is the final stress state of the second layer after the SEM field is placed, right? So all the parameter actually we know already. So we get this value for the TE. Let's put the final. We use this equation, right? Because it's on the OCL line, right? We use this equation, we get this value. Then again, for the TEOP at field, we already calculate, right? We already calculate. So for T equal to 50 years, the S-curve delay is still equal to 0, right? Because it has not reached the TEOP at field. This 50 is smaller than this value, right? So we don't have the S-curve delay for the second layer or for the alluvium layer. So we just use the simplified method to calculate the final result. Okay, this item is equal to 0. This one we already calculated before. S final we already have, and the 0.8 multiplies S final here already we calculated here, right? Here. So we just sum up two layers together to get the final settlement. Okay, to calculate the final settlement. The last sub question discuss why a sixth layer should be divided into a few sub layers for settlement calculation. Okay, this is just for discussion. And now we only choose one point to present the average stress state for that layer. Okay, so if you divide it into a more sub layers, for example, 4 sub layers, even 8 sub layers, you will see the result. The result will approaching, okay, the final settlement will gradually approaching a stable value, okay, like what we discussed in example, maybe example 4 or example, I'm not quite remember, okay, example 4 maybe, I guess, example 5 here. So you can see the final strain will gradually approaching to one stable value here, okay, which means the calculation result is more accurate. Okay, if you only have one layer here, it's like 0.5 for the strain. Okay, later if you divide them into more sub-layers, the result will be more accurate. Okay, will be more accurate. Why? Because we calculate the stress state before and after the SEM field is placed more accurately. Okay, actually the stress state will be calculated more accurately. Okay, if we divide it into more sub layers. Okay, so this is the reason. Just a simple discussion. And I see a question here in the chat box. Why is on 0.4 case not on 0.3 case? Okay, as I mentioned, it doesn't matter 0.4 case or 0.3 case. It doesn't matter. Okay, the 4 here just want to tell you that the final state is on the NCL line, so that we use this equation. Okay, it doesn't matter 0.4 or 0.3. Okay, it doesn't matter. Only depends on where is the point located. Okay, no need to think why 3 or 4. Okay, it's just a symbol. Okay. So this is what I want to discuss with you in today's tutorial, the example 10. I think after I discuss with you, you will be more clear about some details in the calculation procedure. But you still have to go through by yourself, maybe for 1 or 2 times by yourself, okay, to digest the details and then to practice in the assignment, okay? Because this example is quite important. You must have one question, okay, in the final examination, which is similar, okay, to this example. So, okay, I stop recording here.
Recording stopped.
And as I said, I will go through with you the assignment, okay, in next tutorial, next week. So anyway, do you have any question? We already surpassed the time. So do you have any question? You still can send us email, okay, anytime if you have any questions. Okay, if no, the first tutorial we end here, okay, we end here.